semicircle, that you may denote that with different type. Don't be confused over here. This is in fact mr into pi r. Length of the semicircle is semicircle, pi r. Okay. So where m is, what is m? mr is equal to, with the help of this, r square over r6 minus 1. This one. This is r square. R square, if we put z square over here, r square is equal to r square over r6 minus 1. Thus, integral mod of the integral z square or z6 plus 1 dz is less than or equal to pi r cube over r6 minus 1. Or we can write it as pi over r3 1 minus 1 over r6. So when we take the limit r tends to infinity, what is this? 0. This becomes 0. The mod value becomes 0. When r tends to infinity, limit r tends to infinity, this integral will give us 0. Okay, so that means now we have to find only B1, B naught, residue at C naught, residue at C1, residue at C2, and then putting that value in the given equation, we can find the value of the, that is, find the Cauchy principal value of the integral. Now steps 8, find B naught, B1 and B2. So it is not necessary that all the time you have to find B naught, B1, B2. It depends upon the nature of the question. If there is only one singular point inside the contour, then we have to find only one residue. If there are more than 3, then we have to find those. Okay. So here for this particular question, we have 3 singular points. For the residues, we can use this bk, that is residue z is equal to ck z square over z6 plus 1. We can use this formula in the previous lecture. We have discussed the formula for the quotient function. So for the quotient function, we have this residue is what? ck square, putting the value, this is pz, and derivative of this is 6ck5. Am I right? That is the formula, pz over qz. This limit, residue of this at z naught is nothing but pz naught over q prime z naught. This is the formula. We just put this z naught here in this function. We put ck here in this function. So it is ck square. We find the derivative for this function, that is 6z5. So z5 is replaced with z naught. So z naught is ck. So this is the general formula for all the points 0 to 5, k is equal to 0 to 5, but we are required only 3 values, k is equal to 0, 1 and 2, k is equal to 0, 1 and 2. So this bk further simplified to get here, this is 6 c k cube. So b, what is b naught here? 1 over 6 c naught cube. C naught is where C naught is exponential iota pi by 6. So C naught cube is exponential iota pi by 2. This is iota. So B naught is 1 over 6 iota or minus iota over 6. Okay. So what is B1? B1 is 1 over 6 C1 cube. C1 is equal to iota. This is given. So it is 1 over, sorry, this is something wrong over here. Iota cube will be minus iota, sorry for that. This is minus iota, so this is 1. So it is again, this is again iota cube. Sorry. Yeah, that is fine. Sorry, no need. That is fine. This is 6 iota and this is minus. Okay. Now this is 6 iota cube. This is 6 iota cube. Or B1 is equal to 1 over minus 6 iota, or it is iota by 6. And then we have B2, it is 1 over 6 C2 cube. C2 is given to be exponential 5 iota pi by 6. So C2 cube is exponential 5 iota pi by 2. It is cosine 5 pi by 2 plus iota sine 5 pi by 2. So what is this? This become 0 over here. This become 1. So it is again iota. So we have B2 is 1 over 6 iota cube. So we have minus 1 over 6 iota, or it is iota over 6. Right? Sorry? Oh, sorry again. So it is 6 iota simply. Okay? 6 iota. Yeah, minus over here. So but we have two positive. Okay, fine enough. So B naught plus B1 plus B2, it is minus iota by 6 plus iota by 6 minus iota by 6, it is minus iota by 6. So there are 2 pi iota. B naught plus B1 plus B2 is 2 pi iota into minus iota by 6, so it is pi by 3. Thus, limit r tends to infinity minus r to r, f of that is x square over x6 plus 1 dx, it is 2 pi, putting that pi by 3, it is pi by 3. Or this minus infinity to infinity, x square by x6 plus 1 dx is pi by 3. Whereas, what is I? I is half minus infinity to infinity, x square over x6 plus 1 dx. So it is 1 by 2 into pi by 3, so it is pi by 6. So the value of the given integral is pi by 6. Look at the integral. What is the given integral? The given integral was 0 to infinity. We have made that integral half of minus infinity to infinity. So we have evaluated this integral, which is pi by 3. Putting over here, it comes out to be. So the given integral, that means 0 to infinity x2 over x6 plus 1 dx is equal to pi by 6. So if we follow these 8 steps, it's very easy to evaluate the given integral with the help of residues. If you have understood this method, then it's no problem to.
For integration, you can apply some other method.
Yeah, I'm going to that. For example, this integral, particular integral, it's easy. I'm also going for that discussion as well. This is, if you use the real method, it is very easy. We can get the value of this integral within a few steps. That is this x square over x6 plus 1, 0 to infinity. Okay, so it is in fact x 1 by 3 integral 0 to infinity 3x square over x3 square plus 1 dx. So it is nothing but 1 over 3 tangent inverse x cube 0 to infinity. So it is nothing but 1 over 3 tangent inverse infinity minus tangent inverse 0. So this is 0, whereas this is pi by 2, so 1 over pi by 6. So the point is why we have followed the path which is so much difficult. One can ask. The point is that whenever you develop a method, either it is a numerical method or certain other new method, what we do? We usually test that method over the known results. Given known results, we test those methods to make or to get confidence over that method. Okay, that is called benchmark problem. You know already results, then you apply the method, and if you get the same result already obtained, then you say that this method is working well. Then what we do? We go further step, one more, and apply again that method to another known problem, and after applying over a certain known problems, we get more confidence over that method, and after getting the same results for 2, 3, 4 or 5 or 10 examples, we make sure that this method is working well. Okay, no doubt if you follow this method, this is easier. But for a certain class of integrals which are more difficult to solve by following this method, we cannot do that. But with the help of this method, we can do that. If you follow this method, even for a difficult problem, you can get the value of that integral. Okay?